All right, so we're going to continue here today with object-oriented programming, but I did want to bring your attention to, yet again, the Gantt chart here, where you should be as far as your project goes. On Monday, you should have read through the the overall project description, assignment 2 specifically, and the design document requirements. If you haven't done that yet, then you're a little bit behind. Because what you should have been doing on Tuesday is you should have been planning out the rest of your sprint. Now, if you want to follow our Gantt chart, then it's planned out for you. But if you want to have some sort of a custom, like that's not going to take me 3 days to do that thing, then you also need to plan. Then you need to plan out your own custom approach to each one of these phases. Part of that planning process is if you are planning on working with somebody, finding them and working out a communication plan for when you're going to meet, how you're going to stay in communication with each other. But otherwise, today, of course, is your lab. And then for the rest of the week, you should be drafting that first draft of your design document along with designing your test cases. If you design your test cases and submit them this Friday, that is worth bonus points on assignment 2. So make sure that you are fully reading something that you should have been done on Monday, fully reading the handouts for all the details on how to do that. Okay? But otherwise, what are we expecting from that design document? We put several details on Piazza already, but I will draw your attention here to what we're really looking for in order to be able to give you the best feedback on your design. When we say, sketch it out on a whiteboard, what we want to see is basically a sketch of what's called a UML diagram. This is something that you're going to see next week, not this week, but next week in your lab. We give you a UML diagram, and then you have to implement the classes that way. A UML diagram looks something like this, right? So I'm going to go over here to Plant UML. Here's that book class that we were playing around with and that we fully implemented, and that's what it looks like. It's telling me what the name is, what the fields are, the member variables, what the methods are, right? Now, you don't have to get so detailed as with all the getters, right? You could write, it's just a sketch. So you just write out getters as appropriate or whatever. But otherwise, we want to see, how many classes do you have? What are the names of the classes? What are the fields of the classes? How do they relate to each other? For example, we thought forward when we did this demonstration, and we had a demo class that actually executed all this stuff, but we also had a separate utility class that had a bunch of functions to load stuff up from the CSV file, right? We want to see all that stuff that you're planning on doing for your project. So your diagram would look something like this, right? If it was really, really formal. We're only expecting a sketch of this. Ultimately, you're going to replace that sketch with an actual UML diagram generated probably using this tool because it's just a few button clicks and it's installed and it automatically generates stuff like this, right? So remember from Monday, a picture is worth 1,000 words, right? If you draw us a picture with some annotations or something like that, that's enough for us to go on and say, yeah, that looks like a pretty good design, or nope, you're violating the single responsibility principle. And if you do, the rule of thumb here is that the better job that you do on your design document, the more and better feedback we can give you on that design to help you improve it, so that when you actually turn it in and then we evaluate that design, that you get good points on on that design, right? So if you don't tell us anything, or if it's incomprehensible, we're not going to be able to give you any feedback. Okay? All right, questions? No? All right. Then I'll go ahead and get rid of this. Let's review, since it was last Friday that we last touched on OOP, what we were doing the entire time. So we went through this entire week demonstration of developing a book class, realizing that we're going to also want to do the age of the book, so we want a date class, right? But that was already built into the language, so we use it. Also, we want to do authors, and so first name, last name, that doesn't seem like an author to me, so what should that be screaming out to you? Make a class, right? Java is a class-based object-oriented programming, meaning that everything is a class or belongs to a class in Java. So what is a class in Java more formally? It allows you to model real-world problems or real-world objects or entities or ideas, right? Basically nouns. It allows you to group multiple pieces of data together into one logical unit. That's called encapsulation. That's one of the 4 pillars that we'll eventually get to here. It allows you to encapsulate methods that act on that data inside the class where they belong, right? So all the book stuff belonged in the book class. The getAge method, right? What was that, right? GetAge, there we go, right? What we did is we calculated today's date, and then we calculated the period from until today from this release date, and then we returned that as years. Where does this stuff belong? Well, it acts on the data that belongs to the class, the release date of that actual book, and so it belongs in the class. That's what encapsulation is. That's what good encapsulation is. If I had taken these 3 things and put it into a separate function in a completely different class, even if it was the book utility class here, it would have been wrong. It would have been violating encapsulation. Okay? So let's come back over here. It allows you to group functionality together with the data that operates on it. In other words, it allows you to organize code a lot better. Java classes allow you to protect that data from the outside world. Right? For example, over here in the book class, we made everything private. I'm going to go ahead and go one step further here and make everything not only private, but final. Right, there we go. So those coming from a C background will recognize this keyword's behavior. If you use const, right? What is the const short for? Constant, right? It's no longer a variable. Once it's been set, it cannot be changed. Right? So for example, down here, if I try to let's do it up here. This dot title is equal to something, right? It's not going to allow me to even compile now because it's final. I'm not sure what the equivalent is in Python. Anybody know? How do you create a constant? Is it just registering a constant or something in a global namespace? That's how I do it in PHP at least. Anyway, that's something for me to look up later. All right. So now something breaks over here, so maybe I don't want to do this, but we'll do this on the demo later on. Right? Undo. There we go. Okay. Just so that we're not breaking stuff. So it allows you to protect that data from the outside world by making it private, and then only controlling access to it through getters and setters, and preferably just getters, because if you want to create a new book here, call a new book constructor. Right? Don't change it. Prefer immutable data as much as possible. I want to go over one more demonstration here to highlight these 3 aspects of encapsulation in classes for the rest of the day here. All right? To do that, we're going to create a class that models a radioactive isotope. So radioactive isotopes are elements that are radioactive. They give off radiation. If it's alpha decay, beta decay, gamma decay, whatever, neutron decay, right? The various levels of danger to humans. For example, you could go ahead and hold plutonium in your hand and be fine. But if you swallowed any amount of it, you're screwed, right? Versus something with neutron decay, literally they'll put on their drop and run away on radioactive samples like this that are unshielded, unprotected, okay? So one potential radioactive particle here is Strontium-90, which is a byproduct of nuclear fission, bombs, or nuclear reactors. It's an isotope of strontium. Strontium has this atomic number 38. It has an atomic symbol SR, and the isotope name in this case is Strontium-90. It has an atomic weight of, I believe, 90. So it has way too many neutrons or protons or whatever it is. Right? Well, it has a decay period of 28.9 years. The meaning that if you start out with 10 grams in this case of Strontium-90 right now, it's going to take over 29 years to decay down to half of the original, right? So in this case, 4.99 grams. Where does mass can either be created nor destroyed? So what happens to it? It decays into other byproducts, uridium or whatever, right? It just changes into other elements, other radioactive elements, or eventually stable elements. Stable elements are not radioactive. They stay the way that they are, right? All right, any questions on this so far? Otherwise, that's the end of your science lesson for today. What I've got here is a program that is not written in an object-oriented programming manner. It is written in a procedural style. So for example, C is procedural. You have functions, you have, you execute this, you execute that, you execute that. Maybe you'd go through a for loop and iterate and do something over and over again. Maybe you call a function and then you return and you continue on the program, right? That's linear control flow. There's still going to be linear control flow here, but we're going to do this in a more object-oriented programming manner, okay? So for example, what I've got here is a function that decays the mass, right? So given a mass, given a year, and given the half-life, the formula for doing that is mass times 0.5, there's the half-life aspect of it, raised to the power of year divided by half-life. So in other words, if 0 years have passed, your function looks like this. What happens to this expression right here? Becomes 1. And so you are left with the mass that you start with in year 0. After 29 years, with a half-life of 29 years, then this is 1, and we're left with 0.5 to the power 1, which is half of the original mass, right? Thus, giving only 5 grams of strontium-90 instead, right? Undo, undo, there we go. Undo, 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 there we go. All right. Otherwise, what I've got here is just a regular old main like you did in your first program, corn silage or whatever it was, right? And we're expecting 5 arguments. We're expecting the atomic number, 38, the element name, strontium-90, element symbol, SR, right? Those 2 things are strings, right? The atomic number is always an integer because just look at the atomic, the periodic element table of elements, and everything has a whole number. Everything is not exactly a whole number, but that's how we identify them, right? And then we have a half-life in years, which is going to be a double because it's 28.9 years, right? And then an initial mass. And what we do is we record that initial mass, and we start a counter here at year 0. I print out a header here. I don't know if I went over this before, but what is that thing right there? Those of you coming from a Python background will definitely recognize this. 3 double quotes is a what? A multi-line string, right? This is something that was introduced in Java maybe 10 years ago or so, and it's most programming languages where you just have, instead of a regular string with 2 double quotes here, you can have 3 double quotes, and then you can go ahead and spread your string over multiple lines. So that means that you don't have to put in end-line characters, right? Leading white space is ignored, but end-line characters are preserved in your actual string here. So that means that you can actually write a string in Java and make it look pretty rather than having to insert a bunch of control characters, right? Otherwise, we print out this initial header right here. We print out this header of elapsed years and amount, and then we go into this while loop. Why did I choose to do a while loop here? Right? My mass is going to decay, 10, 9.76, 9.53. What I want to do is I want to get down to half of that. So while the mass that I have, right, is greater than or equal to half of the original mass, I'm going to go ahead and print out that mass, increment my counter for year, right, and then I'm going to decay that mass. Whatever mass I have, 10 grams here, I'm going to decay it by 1 year, right, given this half-life that I read in from the command line arguments, right? And then I print it out. That's how I have this nice little looking table here, right? Now that we've seen that as a program, let's rewrite it in a more object-oriented programming fashion. What's the first question you ask yourself, or what's the first thing that you do when you approach this from an object-oriented programming perspective? So what's the first word in that term? Object-oriented programming. O is for object. What should I be doing? Creating an object. In this case, because it's a class-based programming language, means I should do what? Create a class that represents an isotope. Isotope, I got it right. Yep, there we go. All right. So what is an isotope? Let's come back over here to the demo. Let's get rid of the book stuff. All right, let's come back over here. All right. So what, at least as far as this program is concerned, what defines an isotope? An atomic number, element name, symbol, ... those 5 things. Remember, anytime that you have 2 or more pieces of data, in this case 5, right, what should that be screaming out to you? Right? Make a class, right? And that's the last time, hopefully, I'll have to say it, right? All right, so there's our class, member variables. Well, first of all, we want good encapsulation. So should we be making these things public Anybody can read them, anybody can change them, anybody can screw around with them and screw them up. No. Make them private and control access to them through getters and setters. Right? I'm also going to go ahead and make them final. Right? Generally, you should do that anyway, right? Unless you have a very good reason to do so. And we write very good reason here, very good reason, or VGR, right? Only if you have a very good reason, capital letters on all of those, do you make them not final. We're going to have a very good reason here in a moment to come back to this, but for now, I'm going to make it as restrictive and conservative as possible here, okay? Now, I'm not going to take these things in from command line arguments, am I? Right, there we go. So I'm going to have to construct it. How do we construct objects? Using a constructor, exactly, right? So, how do I do that? Well, let me come over here to the isotope. Let's go ahead and go with demo here. I'm going to go ahead and get rid of whatever's in there. Okay. So now let's go ahead and create an isotope of Strontium 90. Isotope Strontium is equal to new isotope, all right? And all that stuff that I had, Strontium, ... right? Except that I have not yet defined a constructor. If you do not define a constructor, like a lawyer, if you cannot afford one, one will be provided for you. A no argument default constructor will be provided. Right? No argument here meaning that I'm not passing in anything to this function call here. Right? Well, that really doesn't help me because if I looked at what this is, system.out.println Strontium, there we go, then it's going to have a bunch of unresolved compile. Okay, what's wrong? All right. Oh, all right. Let me go ahead and take out final for a second here so that we can actually compile this and run it. I'll come back. There we go. There. It's just, nothing gets into that class, right? If I try to do something like, say, Strontium dot, what was it? Element name equals Strontium 90. I won't worry about spelling here. I'm not going to be able to do that because I'm properly protecting that data. You're not allowed to just set it to whatever you want, right? Hello. Does that sound like a valid element to you? No. Right? So come back over here to the isotope class, restore those final keywords, right? Get out of block selection mode here so I can see it. Right? So how do we write a constructor? A constructor generally should be public because you want people to create instances of your class. What's the return type? Is it void? Am I going to return an isotope? Isotope, there we go. Do I have a return type on constructors? Did we have one on books? No. That's what makes it a constructor. It is a very special type of method that implicitly returns basically a new instance of itself, okay? And we know that because we use the keyword new over here, right? It creates an isotope and returns it, so you don't need this explicit return type of isotope constructor returns an isotope, right? So you don't have any return type here at all. If you had a void return type where you're not returning anything, that doesn't make sense at all, right? You're creating an isotope. You have to create something. Right? There's that default no argument constructor. All right, so I can go ahead and come back up here and I can start typing. I'll take an atomic number, right? I'll take a ... right? And then set this atomic number to that atomic number, whatever. Is there a better way of doing this? Let the IDE do it for you. How did we do it with book? Source, generate constructor using fields. All of them are selected, generate it, and it's done. Right? All done. What is that super? We'll get into that when we get into inheritance. Don't worry about it for now. And it automatically generates all this stuff. Right? Well, first of all, before I move on, I'm going to put in a to-do here just to remind myself. You need to write documentation for all classes and all non-trivial methods. Right? Tell me about this constructor here. At least as far as this class is concerned, it is a trivial method. You do not need to put documentation above this. Do you need to put documentation on each one of these variables? No, why? It does what it says on the tin. It's the atomic number, right? If I just done something like this, does that require documentation? Absolutely, right? Don't do that. That's a terrible variable name, right? Radius, volume. What should those variables be called? R and V? No, radius and volume. Exactly. You can afford more characters, you know, right? They come for free. All you have to do is sit there and type them, right? Okay. So here's the demo now. Instead of calling this, whoa, something happened there, right? Something happened that you'll witness in your lab today, right? Do I have that no argument default constructor anymore? Nope. Just like a lawyer. If you can't afford a lawyer, then you go ahead and buy one, right? And in this case, all right, well, I was able to afford my own constructor here because I built it, and so that default no argument constructor goes away. You can restore it by explicitly implementing it if you want. Right? But for now, let's just go ahead and say the atomic number is 38. What else was in there? Element name, element symbol, so Strontium 90. Symbol is SR. Half-life was 28.9 years. They think that's the last one, though, right? Oh, no. And then initial mass. I don't know. 10 grams. There we go. Okay. Now I've got my Strontium. Let's go ahead and try to print this out. Right? Doesn't work. Or, I mean, it works, right? But what is this thing right here? It's a hexadecimal number representing what? The memory location of this object. Just like in Python, if you don't define an str method, right, then you're going to get this weird representation, the memory location or something with your classes. So let me come over here, and I do want to print it out. I wanted to print it out nicely, something that looks like this, right? Atomic name, atomic number, element symbol, maybe mass or whatever. Right? So come over here. How do I do that? Also, I don't like typing here. So source, guess what? Generate constructor using, or not constructor, sorry. Generate toString method. There we go. And generate that. Now, it's not going to look pretty because it's auto-generated code. That's okay. I'm going to steal what I was doing before and put it right here. And then I'm going to string.format. There we go. Exact same functionality of printf style formatting right here, except I don't want that end-line character. And it'll print out element name, element number, element symbol, and maybe also mass. So percent 2f grams, right? And this dot mass. There we go. Oops. I shouldn't call it initial mass, should I? I should call it what? Mass. Ah, now I've got to change it everywhere. What's another trick that we've covered before? Right-click, refactor, rename, and it's changed everywhere for you. I'm probably going to want to change this as well. Mass. There we go. And mass. Wait a second. I'm being inconsistent here. I said this isotope's mass, but I didn't say this element name. That's because it's not required here. But it is best practice to put it in, because the second you forget about it is the second that it starts to go wrong. Right? So let me come up here and show you what I mean by that. What if I didn't have this on that line right there? It still compiles. Right? Well, it compiles, but it doesn't compile, but for other reasons. But there is this warning here now. Right? What does that warning say, if you can really squint here? Assignment to variable atomic number has no effect. How many variables called atomic number do you see on line 18? Right, within scope on line 18. I see one being the parameter, but also this isotope's atomic number. So why is this going wrong? It'd be doing, it's basically that you're doing something like this. Int x is equal to 42. X is equal to x. Should line 21 be there? In fact, there's a warning there, and it's giving me the exact same warning. Right? Take the thing in this variable and put it right back into that variable. It has no effect. Right? Just like this has no effect. What you're doing here is you're taking the value stored in this parameter, and you're putting it back into the parameter. Right? That's not what you want. I want to take that variable value in the parameter and place it into this variable up here. To distinguish that, I use the this keyword. Right? Always use the this keyword, even if it's not necessary, because once you get out of that habit, you get into the bad habit. And once you're in the bad habit, you forget about it when it becomes essential. All right? All right, good enough. Let's come over here and run this now. Strontium 90 38 SR with 10 grams. We're well on our way here, right? Okay, well, eventually I'm going to want to decay that. But I'm going to want, say, several different samples. For example, strontium or sample A and sample B. Because one of them is going to be 10 grams and another one is 5 grams. Okay? So those are actual samples. Here's a sample of this radioactive isotope. Here's a sample of this radioactive isotope. Start the decay, and this one will, they'll decay at the same rate, but they'll have different masses. This one starts out with 10 grams. This one starts out with 5 grams. What about this one up here, though? Wait. What if I don't actually have a sample of strontium? I just want the idea of strontium. Right? In other words, I shouldn't have to give you those grams right there, 10 grams. I just have like the idea of it, right? Okay. Maybe I don't have a sample at all. That doesn't sound right either, right? The idea versus a sample of 0 grams, right? Maybe you want to distinguish those things, just like there's a difference between null and 0, right? Null is not 0. 0 is not null, right? Those two things are nothingness concepts, but they're not the same concept. One is a reference and the other one is an actual number, right? The lack of something. So let's come over here, and you know what? I'd really like to be able to a way to create a strontium or an isotope generally, but I don't want to have to provide the number of grams or the number of kilograms. Am I able to do that with the code that I have right now? No. But could I? Yeah, how? I want a present. I want a functionality that allows me to create an isotope with just these 4 values with nothing specified for the weight, or for the mass, I should say. Well, if you want a present, give it to yourself. Right? So source, generate constructor using fields, and if you want another constructor with just those 4 fields, do it. Right? Now I've got just those 4 fields. Get rid of that for now. We'll come back to that when we look at inheritance. Right? Now this one is complaining because you set that other thing to final. This dot mass is equal to, what do I set it to now? I don't know. Maybe now I have a very good reason not to make this final. And also looking forward here, this is going to decay. It's going to go from 10 grams down to 9.7 grams. 9.7 grams down to 9 point whatever grams, right? So it is going to change. I now probably have a very good reason to change the mass to something that is changeable, right? That makes that go away. But what value does mass have right now? 0. I'm back to where I started, right? I don't want to have to specify it, but I also want to make a distinction between a sample with 0 grams and a sample with an unspecified number of grams. So what do we use for unspecified in, in C? We use null, right? In Python, what do we use? Oh, no? No, we don't have null in Python. We have none, right? Familiar? Yes? No? Okay. You went the entire Python semester without ever seeing none? Okay, all right. The head shake no means that yes, you did, and so therefore you did see none. All right, so this dot mass, what's the equivalent in Java? Null, right? Lowercase though. Except can I assign a small d double the null value? No, primitive types require a value. Okay, maybe I have a reason now to make this a capital D double so that it can be null. Sometimes it's 0, sometimes it's 5, sometimes it's 10, but other times it's going to be null when it's unspecified. That solves that problem. Except that I have another problem now. DRY is don't repeat yourself. Right? You want to repeat as little code as possible until it makes sense, until you have a very good reason to repeat code. I do not have a very good reason here to repeat this code. I've got these same 5 lines, or same 4 lines. I've got these same 5 lines, except that it's a little bit different down here. So I've got 2 constructors. One constructor probably should be invoking the other constructor. Just like in C when we created a factory function, right, and an initialization function, one of those things should have called the others. Right? How do I call, so which one should call which? Right? Which one of these things is more general? The one that takes 5 parameters or the one that takes 4 parameters? Which one can you do more with? Right? 5 seems like more than 4 to me, right? So therefore, this one is the general one. I want this constructor to call that constructor. So what's that constructor's name? Isotope? But that's my name, right? So who am I? Who am me, right? However you want to say it, right? As a human, how do I refer to myself? Me, myself, and I, unless I say Chris, and then I'm talking in the third person, which is weird, right? How does an object refer to itself? Since it's not a person, it's an object, and it uses the keyword this. Or Python, you do anthropomorphize it a little bit, and you use self. Right? So I'm going to call this constructor on atomic number, element name, element symbol, half-life, and then what was my default value for mass? Null. Right? I'm calling that constructor up there. Oops. I changed it to a big D double, and so I need to change those to a big D double. There we go. So no repeated code here at all. If you call this constructor, it takes those 4 things, appends down a null, takes those 5 things, hands it off to this, so you do not have this repeated code. Okay? Now, having those 5 repeated lines, that's not a huge, egregious problem, but this is a much better way of doing it. Right? Much more compact. Okay? All right, now we can come over here to demo, and hey, guess what? Now I can create the idea of strontium without specifying the actual mass. It's now complaining about this because 10 is not 10.0 and 5 is not 10.0 or 5.0. Right? Well, once I add those, now it's okay. All right? So I've got sample A and sample B. Again, DRY, don't repeat yourself. What have I repeated here? 38 strontium 90 SR 28.9. That leads to potential data anomalies. Suppose that I mash my keyboard and this one had a different half-life for some reason because I've typed 8 instead of 9. Right? Any repetition of code, any repetition of data introduces potential failure points and anomalies like this. Let's get rid of that potential failure point and anomaly. What I want to do is I want to take these 4 things and wrap them up and just hand them off to sample A here. Okay? Now, to do that, what I'm going to do is define yet another constructor. A constructor that copies one isotope into another isotope. So, copy this. And it's not going to take those 4 things. Instead, it's going to take isotope, and I'll just call it isotope. Right? You could call it I there if you wanted to, but I is not very descriptive. You could call it that. Right? I'll leave it like that for a second here. But then I'm going to go ahead and rename it, right? What am I going to do? I'm going to copy that isotope into this isotope. How do I do that? Call the other constructor, passing in that dot atomic number, that dot element name, that dot element symbol, that dot half-life, and that dot mass. There we go. That's called a copy constructor. Right? In fact, let me go ahead and rename this now, because that's bad. Don't call it that. Right? Call it isotope. And this is where style becomes absolutely vital, right? What if I had screwed up and called my variable name isotope? Right? Which one's the type and which one's the variable name? I don't know. Undo that. Oops. Isotope. Redo that. There we go. Right. This is why variables are lower camel cased. This is why this is why classes, in this particular case, the constructor, are upper camel case. So you can make a distinction between those two things. Right. That allows me to come over here and not have to copy all those four things. Instead, I'm just going to copy off Strontium. But wait just a second. I don't want to copy the mass from this idea of Strontium, which is null. I want to copy all those four other things, but then have a new mass here of 10. Well, if you want that functionality, what should you want that gift, what should you do to achieve that? Give it to yourself, right? Make another constructor, right? You are not limited in the number of constructors that you can make, right? Unlike, say, Python, how many constructors can you have in Python? They call them constructors, I believe, right? What's it called? Underscore, init, right? Underscore, because it's a magic method. You can only have one. But you can make the parameters optional, right? So what I'm going to do is I'm going to take an isotope and a new half-life, right? Or not a new half-life, but a new mass. So double mass. Right? And I'm going to copy over all four of those things except for that original isotope's mass. In which case, I'm just going to simply pass this on to the other constructor. So that you can create new copies, right? Brand new copies here of this isotope. Oops, I shouldn't have gotten rid of all of that. There we go. And Strontium, right? Wow, look at that much simpler code right now. No repetition, fewer failure points, much more sound code here, okay? All right, now that I've been able to create two values here, let's go ahead and decay them. If I were to just copy over this functionality over here, right? I don't know. Yeah, let's just copy from here to here. Let's go ahead and let's decay sample A here. Right? So instead of printing this out, I'll print ln, and I can print out sample A. There we go. All that stuff goes away. It didn't really go away. Where is it? It's in the class. Why is it in the class? Because it acts on data in the class. So where does it belong? In the class. It doesn't belong here. Right? Then we've got our header. We will need some of the initial mass here. So double initial mass is equal to sample A's mass, sample A dot get mass. Oh, no, I can't get the mass. Can I? Mass? Nope. Can I get mass? Nope. Why? Why can't I access the sample's mass? Because it is private. Okay. Well, now I have a reason here to allow access to the outside world through getters. Select all the getters so that you can get each one of those elements if you want. Each one of those member variables, I should say, not to be confused with the actual element. But I can get these member variables here if you want, but I still can't make changes to it. Why? Because I didn't select all those setters. Generally, you should not have setters unless, again, you have a very good reason to do so. Right? Very good design reason to do so. Right? So, for example, in your design document this Friday, right, if you are going to put in setters, right, you need to provide some justification for that. Why did you do that? If you can't think of a good reason, then you probably shouldn't have done it. Okay? All right, now I've got my initial mass. While sample A dot get mass is still greater than or equal to the initial mass that I started with, I'll go ahead and print out the year and the mass here. So int year, that started at 0, right? And year, and then mass, sample A dot get mass. Right? There we go. And then I'm going to update the mass. But this is no longer a variable that exists outside the class, is it? It's inside the class because I've got good encapsulation, right? So what I need to do is I need to send a message to sample A to decay yourself by 1 year, ... How do I do that? Well, we've got this decay function up there. What I could do is I could go ahead and cut and paste that code over into my demo. And then what I would have to do is I'd have to rip open the element, the sample, pull out the mass, change it according to this formula, and then put it back in there, and then close it back up. Sound like a good approach? Ripping it open just to pull stuff out, pull out its innards just to throw it back in. Right? Surgeons don't do that without a very good reason. Right? So we need to have a very good reason if we're going to do that, and we don't. This method acts on the data, the mass and the half-life, given the year. Where does it belong? In the class. So I'm going to cut and paste this for now and go over here to Isotope. And here is our first non-trivial function, our first non-trivial method. It needs documentation. It's no longer going to be static. It's going to be a member method because it acts on this isotope or that isotope or that isotope. It doesn't act on the class as a whole. It's not going to return anything because what it's going to do is I'm sending it a message, decay yourself by 1 year. So I'm going to change my mass, and I only need the year to do that. Why? Because this dot mass times this dot half-life, right? And then put that into the expression here. That's the result. My mass, this dot mass, is now equal to that result. I've decayed myself. I've decayed myself by a certain amount. Okay? I don't need to return anything. I receive the message. I handle the details. I take care of it. Now, I, in this case, is the isotope class. Right? So over here, I'm not going to rip out all its innards and start examining it just to throw them back in. I'm going to send a message to sample A to decay themselves by 1 year. Sample A dot decay 1 year. How much simpler is that, at least as far as this code goes? Way simpler, right? Way conceptually simpler too. Decay yourself by 1 year, right? How does it work? I don't know, that mysterious formula over there, right? Did I have to worry about it? No. How does square root work? Math.square root. How does it work? Who cares, right? There's some interpolation method, right? It just does it. Right? You don't question your calculator. How are you doing this, calculator, right? No, you just do it, right? Let it take care of those details, right? And then this dot, or not this, but sample A dot get mass. There we go. Let's run this and see if it produces the exact same result, and it does. Right? I did not change the functionality here. Instead, I just made it into a object-oriented programming approach. Right? One last thing here that I want to do is, isotope over here. Let's get rid of all of that now. Right? Let's go ahead and make sure that we are documenting this. Right? So decays this isotope's mass by the given number of years. Okay, well, what if you wanted to do it for 6 months? That'd be 0.5 years. So maybe you have a reason to make this into a double. There we go. All right. All right, fine. Let me get rid of that because it's cruft, right? Oh, decay 1. Decay 1 what? Come back to this in 6 months. Are you going to remember that that was a year? Maybe. Right? 1 second, 1 day, 1 year, 1 millennia, right? 1 billion years, right? Whatever those are. So is a double always an appropriate value? Probably not. Right? Let's come over here to isotope and let's rethink this. Not a year, but a duration. Duration. All right, well, that would be great. That means I need a duration class. A duration class that represents a period of time, right? From, like, it could be 60 seconds, or it could be an hour, or it could be 30 days, or it could be a year, right? Guess what? Just like local date, it is built into the Java time library, right? So by the given number of years, nope, by the given duration. Now, how do I get the duration here? I think it's going to be duration dot get days. Dot of days, 2 days, there we go. 2 days, and then I'll divide that by 365, There are 365 days in a year. Is that very science-y? Are there 365 days in a year? Nope. What are they? It's not a leap year yet, but it will be 2 years from now. Or no, not this year, but next year. So, .25, right? So, whatever your duration is to a standard of like days, divide by 365, and then that gives you the number of years there. Now over here, I've broken the code because I can't just give it one what, right? So what I need is duration dot, what is it, years? Nope. All right, so I'm gonna have to come up here and create it. Duration a year is equal to duration dot of, yeah, there we go, of, and we'll go ahead and go with days, 365, and I don't think I can go 0.25, so I'll just go ahead and hack it here, 365. We'll just say it's 365. I created a duration that was a year, and therefore I can go ahead and give it a year. Hey, a descriptive variable name, right? Do you have to come back for 6 months from now and say, decay, how long? Read it. Decay, a year, right? And because you are using duration here, it is way more precise, right? It's the idea of a duration rather than just some arcane number that you have no idea what it represents. Does it represent a year? Does it represent a date or whatever? Now, we still have that problem before we go here of mass. Here we go. Could it be in pounds? Yeah, it's just a number. Could it be in kilograms? Could it be in grams? What is the standard math? What is the SI? The standard, what does the I stand for? SI units? Anybody, any sciencey heads out there? Standard, is it French or something? SI units? All right, this is going to bug me until we actually look it up. SI units. Standard. Okay, standard units, so it must be French. The I must be some sort of a French word, which would make sense historically. SI express on 7. Come on. Does anybody see it there? Okay. So standard international systems of units. All right, we'll go with that. All right, so the question might be, does Java have a built-in mass library? No. At this point, you get into what's called YAGNI. Oh, maybe I do want to create a class to represent mass that is a universal mass that does conversions all over the place. But YAGNI, you ain't gonna need it, right? That's going a little bit too far, right? And that's over-engineering, right? Only when you need to go far enough that it makes sense for design, but don't go too far and over-design it when you ain't gonna need it, right? So keep that in mind for your design documents on Friday.